And I'm going to introduce Greg Johnson, who is the president of RBR. He just turned his video on so everyone can see his face. Greg, before we start, can you tell us a little bit about what you do in your day-to-day at RBR?
Oh, well, on our Slack channel, I'm known as the chief cook and bottle washer, which probably sums it up. I'm probably better at washing up at work than I am at home, but there we go. Day to day, talking to lots of users of our instruments, understanding how people are using them, where things go great, where things don't go so great, and helping kind of architect the next generation of products that the engineering team is continuously working on.
Awesome. That was great. So I'm sure everyone's excited to hear from Greg. I did tweet about this last week, and I said that I've never had a conversation or seen a presentation from Greg that I didn't learn something new. And I've been at RBR for 2 years, so I'm really excited to learn something new today, as I'm sure all of you are. So I'm going to shut up and let Greg take over.
Great. Thanks, Candace. Yeah, thanks all of you for coming. This is an experiment for us to try splitting it across the time zones. We'll see how that goes. From the familiar faces and names when you haven't gone on camera, I know that many of you actually know a significant amount about conductivity measurements done using an inductive cell. So as it says in the title here, this is a primer. I'm happy to talk about some of the more advanced stuff later on, but it's difficult to pitch these to everybody. So we'll whistle through what is about half an hour or so of slides, and then we'll take questions and we'll see which way it goes. And we're happy to talk about more esoteric things or commercial things or whatever we like. I am just going to make myself disappear so I don't get distracted by my ugly mug. And here we go. So CTDs. CTDs have been around for, well, gosh, quite a while now. And they're really based on two different fundamental physical ways of making a measurement, particularly of conductivity. As you know, it's a weird acronym, CTD, because it's conductivity and temperature, but we don't actually measure depth, we measure pressure. But for whatever reason, CTP never took off, and so it's a CTD. And of course, conductivity is not actually really the ocean variable that we're interested in. We're typically interested at the end of the day in density. And on the way there, we might be interested in salinity. But conductivity on its own doesn't particularly measure anything useful in the abstract sense. In order to use, for instance, the practical salinity scale from 1978, PSS 78, or TIOS 10, which is a more interesting kind of absolute measure of salinity, you really need to be assessing both conductivity and temperature together. And there's a very strong dependence of salinity on temperature, as you know. And so it's important that both of those measurements are not only accurate, but taken at the same time and in the same place. Salinity does have, and density, speed of sound, all the other derived parameters, does have a dependence also on pressure. And so if you're going to profile an instrument through the water column, not only do you need pressure to know where you are in the water column in the first place, but you also need it to correctly calculate salinity, even though that dependence is fairly small. When you're on a mode system, you can simply put in a static value into the instrument and say, you were deployed at 100 dbar, and you can get away with an instrument that purely has C and T. You don't need pressure if you're not going to change it over the lifetime of the deployment. But every vehicle, or let's say vehicular and profiling applications, putting pressure on is essential. So what's the difference in the two different fundamental ways of measuring conductivity? One is that if you asked somebody in high school how to measure conductivity in water, they might first of all think about, well, what is conductivity? And it's just the reciprocal of resistivity. And most people can think about how to measure resistivity or resistance, resistance being in ohms, resistivity being in ohms per unit length, ohms per meter, say. by applying a voltage between two electrodes and seeing what current flows. And the fundamental way that an electrode-based conductivity cell works is exactly that. A voltage is applied between some electrodes, a current flows between those electrodes because of the conductive fluid that's between them. And by measuring either you apply a constant current or a constant voltage, but by measuring the opposite variable, you can derive resistance, resistivity, once you know the cell constant, which converts, it's a geometric factor. And because conductivity is the reciprocal, electrical engineers call the reciprocal of ohms mhos, and that's just cheeky because a mho, M-H-O, is just an ohm spelt backwards. But more correctly, it's known as a Siemen. And so we talk about conductivity in units of Siemens per meter or millisiemens per centimeter, whatever kind of works for you in your head. And getting an intuitive grasp in one set of units is useful. Typically with an electrode-based cell, you have problems of polarization of the electrodes. And so rather than doing it in a DC sense, where one electrode is always more positive than the other, you actually apply an alternating current signal, an AC signal, and make those measurements multiple times back and forth. Now, we'll talk a little bit more about the pluses and minuses of that in a second. But the second fundamental way of getting some current into the seawater so that you can measure how conductive the seawater is to do so inductively. And this is following Michael Faraday's principle of induction. And we'll talk a little bit more about that. But as you can almost see in this picture, there are no metal elements in the seawater in the conductivity cell. There is a red plastic exterior and a white ceramic interior. The only metallic elements here are the thermistor and the pressure gauge itself, neither of which are involved in the conductivity measurement. And so there is no metal touching the water that has an electric current going through it. And that's important, as we'll see later. So we start off by taking a cell and putting two ferrites in it. One is in the bottom of the cell, and it is the drive. And the second one is in the top of the cell, and it is the pickup. And the only way that this pickup sees anything is if there is a conductive loop that attaches those two ferrites together. And because there's no conductive loop in the cell design itself, the reading will be exactly 0 when the cell is in air. So if you ever want to take a drift measurement, for instance, of an inductive cell, simply remove the water. That sounds like it might be tricky, but actually if you're on an ergo float, you just go to the surface. And if you measure in the surface, it doesn't matter if the cell is wet, as long as there is not a single conductive layer all the way around the cell. If that's the case, then you will get a 0 conductivity measurement, and you can assess for yourself any drift that you suspect will be occurring. Now this conductive element is the seawater, and it really behaves like an n-turn to 1-turn transformer. This idea is not a new one, and it was in the 1920s that Picard and Frivold wrote the paper about using an inductive cell without electrodes, as they say, in an electrolyte. And more recent papers, there have been many. So in this schematic, you can see in the red block a little idea of where those ferrites are. Each of those ferrites has coils wound around them. And so we apply an AC current to the drive coil. No transformer works at DC, so you must apply an AC current. That current drives a flux in the ferrite. The ferrite, in turn, will induce an electrical current in any conductor that passes through the center. And in the PowerPoint here, we say it's induced in the seawater, but actually it would also be induced in a wire loop. So if you simply thread a wire through the middle of the conductivity cell and attach each end to make it into a loop on the outside, then the conductivity cell will tell you about the conductivity of that wire loop. The wire loop isn't very interesting, but if you put a calibrated resistance in it, or resistor, particularly one that doesn't have any dependence on temperature, this is a very elegant way of checking the calibration. And in fact, it's how we assess, it's part of how we assess the linearity of the cell in the factory itself when we're building these. In seawater, of course, the seawater conductivity changes according to different conditions. And the current that is passing through that seawater is seen in reverse, if you like, by that receiving ferrite. It induces a flux in that flux induces a current in the receiving coil. And so that current in the receiving coil is proportional, linearly proportional to the seawater conductivity. The fact that it's linear is very nice because it means that you can have a conductivity cell that is got suitable range to measure in salt water, but if you're in estuarine conditions or even in limnological freshwater conditions, the cell works equally well all the way down to conductivities of 0. Ontario lakes are about 100, 150 microsiemens per centimeter, as opposed to salt water, which is up in, depending on temperatures, let's say 40, 50 millisiemens per centimeter. And our cell works equally well in all conditions without requiring any additional calibration or adjustment. So in a conductivity cell, we didn't really show you a picture to give you a scale, but this is something about the size, a little bit smaller than a tennis ball, or a rugby ball combined with a tennis ball, if you like. And so that ceramic channel in the center, which is where the majority of the measurement is made, is fairly short and extremely fat by in a ratio sense. And so we call that a low aspect ratio. The advantage of a low aspect ratio tube is that water just passes through it very naturally. And you can see in this CFD simulation on the right-hand side of the cell advancing through the water column upwards here at about, I think it's 50 centimeters per second in this simulation, that the speed of the water flow, shown by the color, is not degraded in the center of the cell vis-a-vis the speed of the water in the bulk. You can see some boundary effect, of course, around the outside, but we're not measuring significant amounts of conductivity there. The majority of the measurement, over 80% of it, is done in the center. This is a great thing because a cell which naturally flushes means that you measure the seawater without having to do any special efforts to do so. If you make a conductivity cell with electrodes in it, these typically are high aspect ratio. That is to say, they look like a straw. They might be tens of centimeters long, but only a few millimeters in diameter. And as you know, if you try to pass, if you pushed a straw down through the water column, no water is going to want to pass through the middle of the straw. It's all going to flow around the outside. So therefore, when you have an electrode-based cell, and particularly for profiling applications, but even for MAUD, a pump is typically required. And the pump has two problems that it causes you. One that affects some people is that it is acoustically noisy. So if you're going to do any work where you're also interested in listening for sound, then a pump is quite a frustrating thing to have sort of sitting on your shoulder while you're trying to listen for very low levels of sound. But the second and more fundamental problem that affects every user of a pumped CTD is the power consumption. So when you look at the power consumption, for instance, on an Argo float of a Seabird 41, it consumes about 4.5 kilojoules to do a 2,000 meter profile to the surface. It takes about 5 hours. It's sampling at about 1 hertz, generating 2 D-bar bins. But the apples to apples comparison of that with the rbr-Argo CTD, based on the inductive cell, is for exactly the same measurement regime, the same amount of time, the same depth span, we take, instead of 4.5 kilojoules, about 450 joules. So 10% of the power consumption. Now, to be sure, some of that is just a result of more modern electronics, but a large fraction of that is that any mechanical movement driven by electrical motive force is inefficient. And so using a pump, it's very difficult to avoid the power consumption being horrendously high. The other thing that affects you in a CTD that you're going to bring up to the surface is that you have contaminants often in surface waters. They might be oils, they might be other material, and you want to make sure that the measurement is accurate in those surface waters. If you've got electrode-based cells, they get fouled very easily. Microscopic amounts of oil are basically give you an egregious result on the data that you get back. And in the Deepwater Horizon case in the Gulf of Mexico, special cleaning instructions had to be given to people who had electrode-based conductivity cells. In an RBR cell, we are not sensitive to microscopic amounts of fouling, whether that's a physical contaminant or a biological contaminant. Once that contaminant starts to have a significant geometric impact, then absolutely the RBR cell appears to be fouled. And it's not because it's not able to measure conductance or resistance correctly. It's doing that correctly all the time. But it is this conversion using the cell constant from conductance to conductivity that is no longer holding true, because that's really a geometric concern. So we are able to take the inductive cell and measure accurately to within about 10 centimeters of the air-sea boundary, which is quite a nice result. You will always be impacted by bubbles if you're in high seas, but to be able to do that without having any concerns about turning pumps off or any other kinds of factors that you have to take into account makes your life easier. Now, the major downside of an inductive cell is the so-called proximity effect. And that is that we are inducing a current into the seawater, and you can think of it really as a field. And although this current wants to take the shortest route possible to complete the loop, which means that it's dominated by field lines which are close to the cell, there are field lines which extend out actually to infinity. There's a practical limit on how far out those field lines really go, but clearly objects that are near the cell distort the measurement because a small fraction of the measurement is integrated over that space outside. And it depends on the nature of the object as to how that distortion occurs. So if the foreign object, so to speak, is highly conductive, then it biases the reading up. That is to say, salt water is replaced by something metallic that is more conductive, and as part of that spatial integrated measurement, the measurement goes up. If you were to replace that metallic item with a plastic item, an insulating item, then it will bias low. So we have a rule of thumb, which is that we recommend that you keep objects 15 centimeters away from the cell. This isn't, of course, always practical. And so we have a number of ways of dealing with that. The first is that we can calibrate out the proximity effect of anything. So when we supply an instrument with a guard, it always comes with the guard calibrated in, and you don't need to think about that at all. When we supply Argo CTD heads, they always come with their antennas mounted and optodes or other connectors mounted, and we calibrate those out at all. But it's important to have always, and I think this is true across most engineering and science, a sense of proportion. How big is this effect? And is the effect big enough that it's worth worrying about? So here is one of our deep water CTDs actually, clamped to a mooring line. This is a jacketed 3x19 rope. And on the left-hand side, you can see a picture. It's clamped with our standard cable clamps, which are 75 millimeters center to center. That's from the center of the instrument to the center of the cable. On the right-hand side is longer clamps, which are 15 centimeters long. Remember that the 15 centimeter radius is our recommendation for taking items away from it. But look at the table. Our calibration spec, my apologies, this isn't actually in PSU, but it's roughly equivalent to thinking in millisiemens per centimeter. Our calibration spec is 3 microsiemens per centimeter, or 0.003 millisiemens per centimeter. When you take the instrument and you attach it with a 75mm clamp next to this jacketed wire rope, the error is about 2.5 microsiemens per centimeter, or 0.002 in PSU. When you attach the 150mm clamp, the error goes down to a level where you would be highly suspect of being able to accurately measure that at all. A guild line autosal, for instance, the uncertainty in an autosal is typically plus or minus 1 to 2 milli-PSU. So CTDs are a bit of a funny thing. The instruments used to calibrate them are not actually that much more accurate than the CTD is itself. So you shouldn't get concerned about numbers which are below, certainly below 3 zeros, because this is really tilting at windmills. Most people we can help do a calibration to correct proximity. And for instance, if we supply your instrument in a cage, it always comes calibrated to the cage. But depending on your application, you may find that actually this is not something worth worrying about at all. When we talk about accuracy, and the second item should say resolution, and the third item is stability, our data sheets are clear. You know, the range over which we calibrate the instruments is 0 to 85 millisiemens per centimeter. We can build instruments that go up to much higher conductivities, for instance, in brines or highly saline bodies of water. We've done instruments up to about 200 millisiemens per centimeter. But the accuracy on our standard instrument is 3 microsiemens per centimeter, plus minus, and that's kind of a one standard deviation number. That's in line with WOS recommendations, WOS standards. The resolution, not the precision, but the resolution is about 1 microsiemen per centimeter. And in case you're unused to thinking in millisiemens per centimeter, one of the nice things about it is that you can convert it to PSU in your head, and you're not far wrong, depending on the depth and a few other things, but you're roughly within 20% of the right number. So you can convert these to PSU and talk about 1 milli PSU as the resolution. Now, stability on our data sheet, we say is about 10 milli PSU per year. However, that's a very, I'm going to call it a conservative figure, in that we err on the side of caution. And I'll show you some example data of instruments that we have had back for calibration. But first, I will tell you a little bit more about the resolution. So this was some work done by Mark Halverson and some folks from UBC in Powell Lake, off the shores of British Columbia in Canada. What's interesting about Powell Lake is that it is effectively a fjord that was open to the sea until about 10,000 years ago. And then a landslide closed it off. And so you have this body of salt water, but it's been raining for 10,000 years. And so the rain has meant that it's effectively now a freshwater lake with saline conditions in it. It's slightly brackish. And particularly interesting is that it can very often have staircase conditions inside it. So we took one of our standard concertos there, and we attached it to a big frame, and some folks with a slow winch dropped it down to about 350 meters. And you can see in these graphs that there's both C and T as a function of pressure over the section from 325 to 335. So those steps are about 1 meter thick, but uniform. And each of those interfaces is only about 10 centimeters wide. So it's not quite as good as you can get in the double diffusion tank of Ray Schmitz at Hui, but it's pretty interesting. Conductivity is very low. You know, we're in 19 millisiemens per centimeter here. Certainly, I think we're outside of PSS 78 completely. But you can see we've got a Seabird 25 strap there. We've got the Concerto. Concerto is about a quarter of the price of a Seabird 25. And both of them are able to see these conditions. We're running only at 12 hertz, and they are deploying the winch at about 7 centimeters per second. It's a bit slower than, it's on the same order as an Argo float. And so we've got 2 milli-PSU salinity in effective salinity, and 5 millidegrees in adjacent layers. So a nice example of the kind of resolution that you can get with an RBR with no special prep, no data treatment, there's no averaging or anything going on in this data. It's 12 hertz data right out of the instrument. Long-term stability. So we took a group of, I don't know, I think it was about 100 instruments maybe. And they had come back from calibration from users who had had them all over the world in completely unknown conditions. We had no idea how long they'd been in the water, under what conditions they were left on the deck, any kind of cleaning or maintenance that was done to them. But we ran a calibration and we assessed it against the last time we had calibrated those instruments. And here are the drift figures we get. So the first thing you notice is that the histogram here is effectively symmetric. The mean is about 0. So the drift of the inductive conductivity sensor is not a walk in one direction, it's a random walk. The second is that it's quite tightly centered. So 70% of these instruments are drifting at less than 3 milli-PSU per year, 70% of them. And the standard deviation, well, it's slightly higher than that, but it's the same kind of number. So this gives you a feel for what should be happening on instruments that are not necessarily taken care of in any way in particular. We have some float data. On the one on the left, this is the Second Institute of Oceanography in China, in Hangzhou, who deployed some floats. And on the right is Cesaro, who had deployed a, so I think the left one is an HSOE float, and the right-hand one is a web float deployed in the Coral Sea. And using the Owens-Wong stability analysis, we were not able to see any drift relative to the reference over a period of 4 years. And you can read more about that in the JTEC paper that's cited at the bottom there by Nikolai Neslin. We have, in terms of implementation, 3 different conductivity cells, but they're really, as you can almost guess by their size, designed for mechanical strength. So the 6000 dbar unit at the bottom right is the beefiest of all of them, able to withstand about, I think on that one we have about 20% overpressure rating, so about 7,000 meters. The 2000 dbar unit is what we use on the Argo floats, and the 750 dbar unit is used in a conjunction with our POM housings, our Delrin housings for coastal work. All of these have exactly the same specifications. You can see that the thermistor strings are identical. And if you had a very sharp eye, at the beginning of the presentation, when I had a picture of a CTD, you would have noticed that the thermistor sting on that one was considerably narrower than this one. That's because the one shown in this picture is actually our long-term deployment sting. It's made out of titanium. It has a time constant of about 700 milliseconds. I think on the data sheet it says less than 1 second, but it's about 30% better than that. And because it's titanium, there are no corrosion problems ever. Now, we do have a thermistor that's more suited to faster profiling, not to Argo. Argo at 10 centimeters per second is fine with like this, the same with most gliders. But if you're going to profile at 1 meter per second or free fall at 2 to 4, 5 meters per second, then you would benefit from a faster time constant. And so we have a stainless steel thermistor sting, which has a time constant that's about 10 times faster. On the data sheet, it says 100 milliseconds. On the, in reality, it's about 70 milliseconds. Every thermistor, all of the thermistors are within about 10% of each other. And that means that those kinds of numbers, you don't need to individually characterize them at all. So that is really a whistle-stop tour of inductive conductivity, particularly in the RBR implementation. I will pop over to see if there are any questions, and I'd be happy to open it up for comments or discussion if anybody would like to do so.
Awesome, thanks, Greg. We did have a couple questions. You did mention it, but maybe it's good to clarify again. If the conductivity cell is fouled from biofouling, like an algal film, how will the measurement drift?
Okay, so algal films are very rarely are they more conductive than seawater. So they're typically less conductive, and so you will see the salinity freshening. Conductivity will go down. And that's always an indication of biological fouling. That may happen quickly if you are in a highly active area. And for that reason, we don't actually recommend RBR for long-term moored deployments in hot and well-lit environments. And our mission very much is for you to be successful in your deployments. And so we will recommend that you find another solution rather than trying to persuade you of the benefits of something that we clearly know isn't going to work well. Now, on the Argo program, for instance, the float sits down at 1,000 meters for 90% of its life and then comes to the surface once a week. And over 5 years, we haven't seen any evidence of fouling at all on those. We're probably benefiting from the Iridium satellite telemetry, which means that you only have to be at the surface for 10, 20 minutes. Back in the days of Argos telemetry, when it was hours or tens of hours, fouling was a different concern. And so some of you who might be familiar with the old FSI inductivity cell, they really had a lot of problems with fouling on the Argo floats and were eventually dropped. And that's really dependent on how long you're going to sit at the surface. In terms of cleaning off an algal film, please don't go and concern yourself with being delicate. You don't need to get Dow Corning Triton X, which is a special non-sudsing soap. You don't need to use any special cleaning product. Use a toothbrush. You scrape it. There is no effect on the calibration of an RBR instrument to do rough and ready maintenance because there are no metal electrodes. If you were to put a brush on platinum electrodes, even that are platinum black or solid, you will destroy that cell. And in fact, most soaps will cause electrode-based cells to give erroneous readings. In fact, even TBT, which is the carcinogenic antifoulant method that's often used in electrode cells, will contaminate the cell itself. And that's very tricky to determine because that coating happens while the cell is not in the water, and it's a function of temperature that lowers the viscosity of the TBT and helps it kind of migrate through the cell. So depending on what you're doing, you do want to be careful. I'd also watch out for the liability on giving carcinogens to grad students. Next question. Oh, recommended way to clean it. There we go. So that was your recommended way. The only thing I would say is for particularly egregious or adherent, what's the word? A sticky growth. I would use a mild acid. And the mild acid I would propose is vinegar because it's easy to get a hold of. Acetic acid, dilute solution, particularly on the pressure sensor. There are some little holes on the pressure guard to prevent big critters getting in. But you can have calcareous growth buildup on the pressure sensor, and you must never touch the pressure sensor really at all. It's a very, very thin membrane that's sitting above the sensing element itself. In fact, it's about, if you ever come across a broken one, they're fascinating to take apart. The membrane is about 10 microns. And so it's almost like you look at it and you dent it. Please don't ever stick Q-tips, screwdrivers, fingers, other things in there to clean it off. Leave it overnight in vinegar and then rinse it with fresh water. We find that there's not much that resists that. We do occasionally for instruments which come back after many, many years in the water, we put them in an ultrasound bath just to vibrate off some of the worst stuff. Chemical ways of cleaning, yeah, don't use anything harsher than vinegar. Yeah.
While we're on the topic of antifouling, Kurt is asking me about coatings to put on the conductivity cell.
Ah, okay. So in general, you don't want to put anything on the cell that is going to change its geometry over time. So you could coat the cell, for instance, in zinc oxide, like nappy rash, what do you call it in North America? Diaper rash cream. For those of you who are parents, you know what I'm talking about. And that's often used, for instance, on ADCPs and on the transducer heads. Some people use chili paste. There are all kinds of creative antifoulants. You can put them on the rbr conductivity cell, but I wouldn't advise it. And the reason is that you're changing the geometry of the cell. But you're not doing so once and for all time. Most of that material is going to slough off over the months that it's in the water, and so the geometry will change. It's one thing to put on a coating that you can calibrate out the effects of the coating, but the coating doesn't change. But if that coating effect changes over time, then you're really in trouble. And the same is true even of copper-based paints. Apart from the whole question of how conductive is the copper-based paint, and are you bypassing the electrical circuit by giving it basically a short circuit to get back, most copper-based paints also slough off over time, as those of you who have to anti-foul boat bottoms know well. So generally, we wouldn't recommend anything like that. Some people have had success in terms of putting copper mesh around the guard, for instance, in very active areas. And those are areas where typically you're not looking at very small signal in any case. And so it's a bit like this question about the proximity effect. Your sensitivity to it is less. One thing to note is the correction for putting in place any kind of object in proximity in salinity is purely an offset. So if you've got a bucket of water that's well stirred and you measure salinity, and then you attach your very, very close metallic frame to the instrument and you measure salinity again, you'll get a difference between the two. You can use that as an offset across the entire measurement. So in salinity, it's an adder or a subtractor. In conductivity, it's a multiplier. So you just need to remember it's easiest to do it in salinity because it's an adder. And it kind of makes sense that it's a multiplier in conductivity because clearly when you go down to 0 in conductivity, there's nothing you can do to it to make it more conductive.
Yeah, Greg, the only thing I was going to mention was that one thing I've been thinking about trying, but over the years, we've never really gotten around to doing it. I had talked to Chris Contos about it at one point. There's a company called Clear Signal.
Ah, yes.
That makes clear, durable anti-fouling coatings, primarily for ADCPs. I mean, we've had a couple of our ADCPs coated with them, but actually, we've never actually deployed them. But this is something that I've been thinking about for coral reefs work, because any cylinder, any conductivity CTD that you put in the reef is going to get fouled, whether it's the seabird or the RBR. And I've like I said, we haven't gotten around to doing it, but it's something I just wanted to point out, something I've been considering. And Chris just said, you know, we'll send you the instrument, you send it off to Clear Signal, we'll get it coated, send it back to us.
Yep.
And we could get it
recalibrated,
so to speak. I'm curious what your thoughts on that are. Does that seem reasonable?
So Hank Loeb and Seven Marine, who make Clear Signal, have been, promoting it for at least 5 years now. It went on a Rutgers glider that did a transatlantic run. That seemed to have reasonable results on the glider hull. This was at least 5 years ago now, and it does seem to work pretty well on ADCPs. The question in our mind has always been the guarantee that it doesn't slough off.
Right.
Because, and also initially, they were, so I feel like there is now a way of people being able to apply the coating themselves. In the initial days, you had to send it off to them. And so at the moment, yes, if you were able to send us an instrument that had been coated, we'll happily throw it in the calabash. And sorry, I'm staring at the side of the screen because that's where your picture is. But
yeah, no good, no worries.
We'd happily check it in the calabash and see where how it goes.
Yeah,
what would be even more interesting is to check it after deployment.
Right.
And I know that they also did some work with Turner Designs on coating the fluorometers, but I think they had some problems with the optical transparency of it. Although it by eye is clear, and clearly when you're working with a fluorometer, it's not.
Right.
I think that there are a number of techniques, chemical, mechanical, wipers and plungers, that kind of thing, like kind of chimney sweep arrangement. There's also using UV is to do anti-fouling. But the problem with UV really that nobody is going to overcome is that UV LEDs are too inefficient. For every watt of electrical power you put in, you get less than a milliwatt of photons out. And so they're right at the edge of the spectrum for solid state light emitting diodes at the moment. And just in the same way that when green LEDs came along and then blue LEDs, and we got Blu-ray DVD technology, and it, the shorter those wavelengths, they were tough to make. And the yield was terrible and the efficiency was terrible. Once UV LEDs get to the state of much higher efficiency and the prices coming down because of the yield going up, then I think that's going to be a viable technique. We've done a lot of work with UV LEDs, and in cabled observatories or mooring systems where you have a source of external power, they're ideal because they're very effective. You can adjust the dose. It's completely localized. There's no net long-term effect on the ecosystem. I can't imagine anybody contemplating putting TBT on a coral reef these days.
That's totally not allowed. But so on that note, then, is it only the center of the conductivity cell that would need to be kept? Really, the whole thing needs to be kept free and clear, right?
That's right. So you need to illuminate the whole thing. But we use this 80-20 is a rule of life, really, and 80-20 also happens to be about the right proportions for the rbr conductivity cell. 80% of the measurement is taken inside the cell, 20% is around the outside. So if you can keep the inside clear, you've already fixed 4/5 of the problem. The outside would be the last fifth. So yes, you would like to illuminate the whole thing, but even something would be better than nothing in those highly active areas.
Cool.
Rick, I see. You've got a question about FSI and RBR. So the FSI inductive cell has quite a bad rap, it's got to be said. It got dropped off the Argo program probably about, I don't know, quite a while. And Rick, you probably know actually better than I do when it got dropped off the Argo program. Are you able to come off mute and tell us? Oh, maybe Rick only has a speaker and no microphone. Yes, okay. He built a majority of the floats. So, Rick, I mean, I think I wasn't deeply involved at that time, but I think there were two failure modes. Oh, we want to see your kids just like we can see Kurt's boy there. Let's bring your boy to work today. Hello, young Rosenberger. Oh, hello, Mr. Rupan and Mr. Rupan Jr. Oh, it is Bring Your Boy to Work Day. That's great. So, Rick, I think there were two primary failure modes for FSI. One was that the fouling was egregious, and two was that the firmware was atrocious. And I think the firmware problems related to the pressure binning being done incorrectly in firmware, and it was a non-reversible calculation, which meant that once the data came back and that you couldn't actually fix it. I might have those details wrong, but I do recall people like Howard Freeland telling me from iOS in Sydney, just north of you, or across the, anyway, Rick is in Seattle and Howard's in Victoria, and they're pretty close to each other. Howard telling me about recovering some floats that had FSI cells on them, and they were just covered in barnacles. And that was fundamentally not because of a mistake that FSI made, but because they were staying at the surface for so long. And we've really benefited from the developments in commercial telemetry, satellite telemetry. The Iridium system has the bandwidth and will have more bandwidth to stay at the surface for a relative short period. And that's why we're not seeing any fouling on floats that have rbr-CTDs on them at all. So
Greg, may I ask a question? If I remember correctly, the one of the selling points of the FSI was that it had a dual inductive cell, and therefore they were able to eliminate the proximity effect.
Yeah, so they had a variant of it. It wasn't the one used on the Argo float because it wasn't necessary. And the variant is called Nyxic. Well, I pronounce it as Nyxic, N-X-I-C, something like no external inductive current.
Non-external,
cell, something like that. And the principle of it is to have two cells co-located inside one bigger cell.
Yeah.
And one cell would push a current out, and the other one would pull it in. And that bigger cell then, by Kirchhoff's current law, which is used to say that current has to go somewhere, if you're pushing current A out here and you're pulling minus A down here, then by definition, at the aperture to the bigger cell, no current can be going out and returning round to the bottom. And that's the principle of the Nyxic. So it contains the field inside the larger cell. It's a nice idea for a mode design. However, it's very tricky. Well, and the reason it's a nice idea is because then you can copper clad or diaper rash coat or chili paste or whatever, the entire outside of the larger cell, because it just has to be an effective biofoulant. It's never going to see any induced current, and therefore it doesn't matter if it changes over time. Right. So for more deployments, it's a nice solution in theory. The problem is in practice that pulling a current that is exactly equal to the pushed current caused by the seawater loop is very tricky to do electronically. And that's why Teledyne, for instance, acquired the FSI CTD line and rebranded it as the Citadel. And they have just, I think, they've had it for 4 or 5 years, and they've said enough. Like they can't.
Yeah, they've abandoned it.
They've abandoned it. Yeah.
Yeah. Okay. I was just curious if RBR had ever considered that,
Oh, we've got all kinds of things in the labs, but some of those things that we talk about are, you know, it feels a bit like how many good ideas did Apple have that never released? Well, I'm not sure our ideas were as good as Apple's, but certainly we've had lots of ideas where we've taken them as far as they can go and moved on.
Yeah. Thank you.
No worries.
That's all the specific questions in the chat, but I'd like to invite people to turn on their mics and their cameras, especially if you have kids, because that makes me really excited to see the kids on the call. And you can ask questions directly, and like Kurt's been doing, it's been great to be able to hear directly.
And it's great to see so many familiar names on the call as well. You don't have to have brought your kids in order to qualify for going on camera. But I'm seeing people from all over the world here. So thanks very much for coming. Oh, here's a brave one.
I have a question. Can you hear me?
Yes, we can hear you, Chris.
So I'm curious about how close you can get to the surface. How much of it needs to be submerged? How much of the field needs to be underwater?
Yeah. So the Argo program was also curious about that. The Argo spec for the CTD is actually slightly more relaxed than WOS in that it's 10 milli-PSU rather than 3, which is what we can get in the lab kind of thing. That 10 milli-PSU, so the way we do this experiment is we take a bath of our conductivity bath, which is salt water that's well stirred, and therefore homogeneous. So regardless of where the instrument is in the bath, it should make exactly the same measurement. And we put it in the bath with the sensor facing upwards. So the sensor was going to approach the surface first before the body of the logger. And then we took a measurement that was really proportional to distance from the surface, and we looked to see when it changed. And so it starts to change at about 15 centimeters from the top of the cell to the air-water interface. And at 15 centimeters, it changes by about 3 milli PSU, 003. By 10 centimeters, it has changed by 10 milli PSU, which is the Argo spec. So that's the number that we most often quote. It's because it's usually in talking to Argo scientists. How close can you get to the surface and still be within the Argo spec? It's 10 centimeters. But actually, the more correct answer is 15 centimeters if you need 3 milli. Now, lots of other things factor into that and make that an implausible measurement case. And that is that that's only good if you're in still water that doesn't have a lot of bubbles entrained into it. Once you have bubbles entrained into it, every conductivity cell in the world is doing a volume averaged measurement. And that volume averaged measurement sees bubbles as perfect insulators. So if you've got 50% bubble and 50% water, your conductivity reading is off by 50%, and there's nothing you can do about it. So you want a cell that, well, you certainly don't want those bubbles to adhere and stay there. Fortunately, most profiling instruments go down, and those bubbles just get disappeared, and then the gas dissolves into solution. So you can take that, you know, for what it's worth, which is in still water conditions where there are not large bubbles, you can get accurate measurements to kind of the 10, 15 centimeter level.
And would orientation matter? Like, could you bring it up and put it sideways near the surface, and would that change anything?
Yes, but not significantly. The flow lines do come out the top, come around the side and back in the bottom. They're obviously slightly asymmetric because the bottom has the housing of the instrument, and so the flow lines, the current lines can't pass through that. What else? Yeah. So yes, there would be a slight difference if you came up sideways. I'm curious though, can you tell me more about your application? Is this a curiosity question?
More of a curiosity question. We have every year take students to Banfield for a field course, and there's always someone who's trying to measure as close to the surface as possible. And as you know, Rich Pavlovich is always interested in getting as close to the surface as possible. So yep. More of a curiosity question about how those numbers and how accurate they are. So thank you.
The trick is, of course, when you're on the surface and you've got the instrument attached on a line, is how do you get the conductivity cell to be face up?
Would it not work in facing downwards with the same, like the bottom of the cell would be 10 centimeters below? Would that not?
Yes, broadly speaking, yes. The difficulty is just that you've got that whole instrument behind you. And so it's not quite such a symmetric thing. The other way, you can check it yourself. The other way you can check this is by taking a tank of water and dropping the instrument to the bottom, because when you approach the bottom, you'll start to see that measurement change as the flow lines impinge on the plastic bottom of the tank, or the brick or the concrete or whatever it is.
Thank you.
No worries.
Greg, Jess was asking if any of the 6,000 decibар cells have had a chance to be integrated on a deep Argo.
Yeah. Good morning, good afternoon, Jess. Yeah, so Teledyne Web is currently doing a float with our 6,000 meter cell and a Seabird 61 side by side on a deep apex float for Brian King at the National Oceanographic Center in Southampton. Fritz Starr, who you can see with his smiling face, is on this call from MRV, and Neil and the rest of the team over there. We've been talking about putting it on the MRV Deep Solo float, which is another 6,000 meter float with excellent reliability figures. They've got lots of deployments due to the Paul Allen Foundation money. And so there's quite a lot of interest there. We've also done, let's see, there's also a float manufacturer in China who is doing the same thing with a glass bottom boat, glass sphere. So it's early days, I think. There are no deep Argos producing fantastic CTD data that I'm aware of at the moment.
I'm going to stop recording because I'm cognizant of time, but I'm not going to stop the conversation.